Hello and welcome. Welcome to our professional learning coding series. My name is Melissa and I am lucky enough to be your blue coat. I'm going to be walking you through this lesson today. Our lesson is called Gears Rule. Now, just before we get fully ramped up and going, I would like to acknowledge that we are on the traditional and ancestral lands of the Atikameksheng, Anishinaabeg, and Wanapitei First Nation. We would also like to acknowledge the Métis Nation for their cultural and economic contribution in this area. These lands sit in the Robinson-Huron Treaty area, and as we are all treaty people, it is important for us all to be thinking about what treaty area we live in and are an active part. So let's take a moment to appreciate the land that we are on by acknowledging the traditional territory and treaty area that you are located in. So this is the land acknowledgement for me here in Sudbury, Ontario, and as this is sort of a province-wide stream, then you may be in a different land. So just take a second to acknowledge that. So I introduce myself. My name is Melissa. I will be leading you through this lesson here. With me also sort of behind the scenes, I have Brendan. He's just gonna pop in for a second, but he is there with me. He'll be taking comments. So as we go through this live session, you can pop comments into the chat and we can either answer. There may be one of two ways we'll answer, either commenting back to you within the chat, or I may answer your questions sort of throughout the video. So awesome, thank you, Brendan. Now, the first thing I just wanted to quickly highlight for you to be able to refer back to afterwards is our resources on the Science North website. So we have a team of people in what we call our sort of education unit, and we put together resources for classes, for teachers. Now, what I'd like to just highlight quickly here is how you can find the resources for today and tomorrow's sessions. So I will stop my screen here, back out here. So here we've got our sort of the main Science North landing page. So at sciencenorth.ca, you can see we've got a Learn tab. So the Learn tab is going to drop down a menu, and where we want to get going, we want to go to Schools. So here's our Schools page. The offerings that we at Science North have put together this year are obviously a lot different. So we have virtual learning packages rather than sort of on-site packages. And what we are doing for teacher professional development is also different. So at the top here, we've got this Teachers tab where we have a little video about our teacher workshops, which aren't happening in person right now. And if I scroll just a little bit further down, we have this education.sciencenorth.ca tab. So this is where the educator resources live. If I pop into here, you can see there's a few more tabs, folders with different resources. In videos, there's a bunch of different videos intended for teachers and for classrooms. So there are videos on different topics there, but what we are covering today is this professional learning coding series. So right now, our grades 3-4, November 23-24, that's today. So this is the bank of everything that you're gonna need to be able to put on this lesson. So our goal is to make it as easy as possible for you to either grab the whole lesson if you like it as is, grab certain parts of the lesson, and sort of make them your own and integrate them into your classroom. So I have like a ton of respect for you and your profession, and what I get to do sort of tangentially in these times is get to sort of support. So that's been fun and exciting for us. So I'll pop back into my presentation here and talk about Gears rule. So our workshop goals for students, we're dedicated to getting students excited and thinking about science. So we do that by, innovative hands-on activities. The very first thing that we're going to ask ourselves when we're designing a workshop is, what are people going to be doing? What is the student going to do? So that's sort of weaved in everything we do at Science North and, applying to these coding series. So the Gears rule lesson that I'm going to walk you through today and tomorrow is going to be broken up into 2 parts. So introducing the concept and applying the concept is what I will be covering in today's session. Tomorrow, I'll be going over the culminating math activity. So we're looking at right now just the list of those resources that we will be using over the course of today's lesson and tomorrow. So tomorrow, the culminating math activity, we're going to get into the nitty-gritty into a coding program, a block coding program. So I will walk you through sort of how the program works and apply our Gears activity in that program. All right, so gears. I have an image of a gear here. Gears are kind of like, they're beautiful and amazing. There are tons of different kinds of gears. I picked this image here because it's so shiny and, really, really aesthetically pleasing. There are many, many different kinds of gears in the world. I made a list here so that I could remember there's spur gears and helical gears, spiral bevel gears, screw gears, worm gears. At the core, each of these different types of gears is intended to change a movement. So we have some kind of input in, and we're going to change either the speed or the direction of the movement, and in turn, sort of the force that comes out. So gears, a simple gear system on its own is, beautiful and complex, but once we really start to put gears together in a train is when we can sort of see their full potential. So if we think of some examples of gears, things that we know have gears in them. So I think like a watch. We have a certain input, and we want to have different hands turning at different speeds. The hour hand is going to turn at a vastly slower rate than the second hand. And so you have a complex gear train that's going to slow down the movement. So you have an input and you have an output. If you think of gears on bicycles or gears in a vehicle, oftentimes one of the trade-offs we say, if the gear is going to go faster, then it will have less force. So you can imagine in a vehicle, if you only had a small number of gears, the range of speeds that a vehicle would be able to attain would be a lot narrower. So more gears gives us more speed with more force, excuse me, more force output. So there are many complex gear systems. What we're going to confine ourselves to today is sort of 2-dimensional spur gears. So these are going to, create sort of like a rotary movement. And when we put the gears into a gear train, so we have gears one after the other, these gears are going to follow a pattern. We're going to be able to predict the motion of a gear in a series based on the motion at the beginning. So this ties into your math curriculum. You've got, patterning and algebra. If we can predict, the elements of a sequence, that's an important thing in coding as well. Kids often think like, oh, coding's like computer games. Well, if you have a simple computer game where every time you hit something, you get 5 points, well, identifying a series where you can add a +5 is really important. So for us here, we're going to be identifying the rules that gears are going to follow and applying them to coding by using conditional statements. So conditional statements are like an instruction. It's an instruction that you give a computer, and it allows the computer to make a decision. And it's a crucial part of any sort of coding process. So I have here some sort of conditional statements. This logic often follows an if-then form. So if a certain condition or statement is true, then you'll have sort of input output. So in my examples here, if the fire alarm goes off, then the classroom has to evacuate. If I arrive to school late, then I need to stop at the office before I go to class. If the bell rings, then, well, this is a kind of an interesting conditional statement because it needs a little bit more information. So obviously inside a computer, it's going to have a number of if-then statements that help it to make a decision. So you can imagine if I press the power button on the computer, then, well, if it's off, it's going to turn on, but if it's on, it's going to turn off. So there could be more than one sort of if-then option. So we want to just go through these examples that can apply to different situations in life before we get to the gears. So I put some examples up here. Now, they may be things that your students will sort of that would be maybe more relatable, that might resonate more with them. So yeah, I would say there are a ton of different ways to look at these if-then statements. So here's a few more examples, like about gadgets and things that just sort of to get our minds into the if-then logic. And now we're going to look at how it applies to gears. So in this sort of simple example, we have a number of we've got 3 gears in a train, one after the other. And what we want to do is sort of look at how the movement goes in order to sort of find out what those rules are. So the rules are basically the gears are going to behave based on the laws of nature, sort of the laws of physics. But how can we write those out into a simple if-then statement? So if we look at the gear here, so we've got 3 different gears. They're sort of different sizes. This red arrow represents the force. So if the force is applied in this direction here, we've got a clockwise motion. So we've got clockwise motion in the first gear. We can sort of see that the next gear is going to get pushed down in the other direction. So it's going to go counterclockwise. And if we sort of follow the motion, once we get over here, if this gear is going counterclockwise, it pushes this gear to go clockwise. Clockwise, counterclockwise, clockwise. Yeah, and that's sort of the pattern that the gears are going to follow. Each successive gear is going to go in the opposite direction. And that's sort of one of the rules that the gears are going to follow. Now here we have another example where we have a large gear and we have a small gear. So all of the conditions that we are going to be sort of, the rules that we're going to be writing today are, we're not going to be looking at the numbers aspect of it. So when you count the number of teeth on a gear, you can predict accurately and to the number, how the gears or how the motion is going to be related one to the other. What we're doing today is looking at the motion in more of a qualitative sense. So will it be slower? Will it be faster? Rather than getting into sort of the nitty-gritty numbers part of this. So like I personally find like the intellectual gymnastics when we use fractions is pretty satisfying, but it's not going to help us to understand the concepts at this stage. So Yes, we can make accurate number predictions by getting into gear ratios and counting the numbers of teeth when we're comparing movement. But for us today, we're strictly confining ourselves to that qualitative sense. So if we've got a big gear, we've got an input force on a large gear, what does our sort of output look like here on the smaller gear? So we're having a clockwise motion. So from the last slide, we know that this gear is going to be turning counterclockwise. And actually, this gear is going to be moving a lot faster. Okay? So when we go big to small, we get a faster motion. So at this time, I want to pull up a program. It's called Gear Sketch. So it's like a little web-based program. And I'll just want to swap the screen so you can see where, follow along here. And Gear Sketch right here. All right, so it's a very simple program. And what I really like about it, it's cool. So it's like somebody else has done the work of sort of coding the rules into this little program. And what it's going to allow the students to do is explore and test out some of their predictions. So it's very simple in that you can draw a circle and it makes a gear. So you can sort of experiment. So if I have, I want to see what happens when I have a big gear on a small gear. Okay, what does that look like? Well, nothing, if I press play here, nothing's going to happen because I haven't applied a force. So you saw that it said add some arrows. Well, one of the rules that we can actually write is if a gear doesn't have a force applied to it, then it will stay still. So we need to add a force. So let's add a little bit of a force here. So we are telling now the program to run the big gear clockwise. And we can see that the little gear is going counterclockwise. And another thing that we can observe here is that the second gear, the smaller gear on the end, is turning faster. So if we drag the arrow like bigger here, we're changing the amount of force. So if we press harder on the big gear, well, then we get faster movement on the big gear and even faster movement on the smaller gear. So this would be a great time, I think, to sort of allow students to just explore within the Gear Sketch program. So a neat thing, you can just sort of scratch out your gears, add more. So now if I have, I've got one, and then another, and then another. There's a short little gear train. And now I can see what happens. So now I've got a small input gear and I've got a large output gear. So what we can see is that the large output gear is moving a lot more slowly than that smaller gear. And typically, if it's moving more slowly, it's going to have more force. So now what happens if I add now another gear? So I can see, again, as I'm adding more and more gears, that pattern of clockwise, counterclockwise, clockwise, counterclockwise, sort of, and so on. So I just want to restart. It's just very elegant in how simple it is to create these gear trains. So if I want to do, see it now. One thing that I have noticed, if you're trying to do this on a laptop with a trackpad, it's really hard to draw a circle. So you kind of need a mouse or something that you can drag. So I've got this time here, I want to sort of stack them. So if I've got a gear here, and now I've got a second gear sort of on top, So they're going to be turning together. So if this one's turning this one, then this one will also be turning counterclockwise. If they're turning counterclockwise, if they're turning clockwise, then they both will turn clockwise. So I can like add a gear here. Right, so what will happen if I do this? So there are, again, a bunch of different ways that you can sort of experiment with the different motions. Now, one sort of last thing that you can do within this program, whoops, I hit something there as I was trying to make that, but it still worked. That was great. So you can add a chain. And this will allow us to create rules that, what's going to happen to the gears when they are attached sort of by a chain. What happens to the motion? So we can actually see here that the motion is in the same direction. So there's really not a right way to do this. I think it's a really good opportunity to do some sort of, investigative and exploratory learning with the Gear Sketch program because it is so simple. There is even the question mark here will show just a quick little video also of how it works. So from the Gear Sketch program, so once students have made their own little gear sets, their own gear predictions, then we want to move to the handout. So within the resources that are online, the handout is in that little package. So I'm gonna pop back into my presentation here. And here's where we're going to write out the different gear rules. So today I'm going to go through each of the different rules that are written out in the handout, and then I'll go to the next sort of document activity is an assessment. So if a gear, sorry, I was like, let me, what is my even if statement this time? Okay, so if a gear does not have a force applied and is connected to another gear. So this condition actually I talked about a little bit earlier, then both gears will stay still. So in the image here, I do have a force applied, but this is this is a thing that humans know. You know that if you don't push it, it's not gonna move. But this is a rule that you have to tell a computer. So some of the things that we think are super obvious, well, because we're humans and we have the knowledge of having the experience of having lived on this planet and knowing what those rules and laws are. But again, computers don't. So it seems like an obvious thing that wouldn't need saying, but a lot of times that does happen within coding. So if a gear doesn't have a force applied, then both gears will stay still. If a gear has a force applied and is connected to another gear, then both gears will turn. So within this handout, the prompt is it says, write the pseudocode. So the pseudocode is really just a set of instructions. The code itself, it would have some syntax, it would have brackets, it would have, that's one of the things that can sort of be frustrating about coding. So by writing a pseudocode, you're just using words, you're not using any symbols. And it really allows us to get familiar with the logic, the type of conditional statement that we might use and sort of that language. So in the handout, rule 1 has an image here. So we've got, we can see the force applied, and we can also see that other gear is going to go in the opposite direction. So one of the rules that we can write, if a gear is turning clockwise, then we've discovered through Gear Sketch at this point then the gear next to it turns counterclockwise. So most of these conditional statements kind of have an opposite that is also true. So if a gear is turning counterclockwise, then the gear next to it turns clockwise. So that's its sort of, I want to say, like sister rule there. So now our if statement, if a gear is smaller than the gear next to it, then in comparison to the first gear, it moves faster. And that we could see really well within that gear sketch program. So again, the opposite of this rule will be if a gear is larger than the gear next to it, then in comparison to the first gear, it moves slower. So again, that's that like flip side of that coin. So here I've got the third rule here. So we got to specify. This is one of them that needs sort of like a, an extra in a gear train with no belt, like an extra little bit of information in order to. So if there are an even number of gears, then the last gear moves in the opposite direction as the first. So I just want to take a quick little second here. I'm going to sort of swap my screen to the document itself here, just so you have an idea of what it looks like, sort of from the handout for the student perspective. Over here. So actually, the document that I've got up right here, it's got the answers. So I've pulled up the teacher solution here. But what I would like to do is pretend like it isn't done. So in the handout for the students, you'll have sort of, you'll have if a gear is turning clockwise, then the gear next to it turns counterclockwise. So you will have that written rule, and the student's activity is going to be to draw the rule. So what I'm showing right now in the PowerPoint, I've got the drawing and I've got the pseudocode. I see Brendan is smiling at me from behind the scenes. Does he want to pop in for a second?
I can pop in. Sorry, Melissa.
No, thank you.
No, I just wanted to mention, hence the smile, that the answers are not provided right away with the churning either, so that they're not told as counterclockwise. So really, this is an inquiry-based activity, and the idea is that a student is given the rule: if a gear is turning clockwise, they have to go in gear sketch and figure it out, and figure out what is happening as a result. So we created this as an inquiry-based, let them figure out the answers instead of giving it to them, so that they're kind of forced to go on gear sketch, apply these conditions that they have, these if statements, and then figure out for themselves what the then are. And then once they have the then statement, fill out that blank, fill out the drawing, and then write the pseudocode to represent that. So, sorry,
it backwards, but no, thank you. I appreciate that, and I'm sure all of the viewers will appreciate that as well. So,
all right. Anyways, keep rocking it.
So what I'm going through here are sort of like all of the answers. Where the students will not have these, they will be challenged again to go into gear sketch and figure them all out. So rule 4 here, we can see you've got the gears. If 2 gears are connected by a belt, then the gears will move in the same direction. Now this is a little bit different than the other rules. As I was mentioning, you had sort of you had two sides of the coin. Well, there isn't really an opposite here. So if you turn in the opposite direction, well, the two gears will still be moving in that same direction. Now our fifth rule here, if the size of the arrow gets bigger, then the speed of the gear will get relatively faster. So now if we have two gears are connected and both have a force in the same direction. So this one's kind of tricky here. It's like, well, whichever size, whichever gear has the bigger force is going to determine the way in which the gears move. So it's like, if the forces are competing, whichever one is bigger is sort of going to be, I want to call it like the winning force, and its direction is going to sort of take over. So once the students have completed that handout activity, the second activity is to use those rules that were written out to make predictions on these sort of longer gear chains. So in the handout, let me just double check that I have the right one open. And I do. So let me just bring that up so you can see it. So this is what it looks like here. This is the student assessment. So it's going to show each of the gear trains, and it asks for each of the successive gear trains to make a prediction about the last gear based on what you can see, what you can observe from the motion. And the last gear, you want to make a prediction about whether it's going faster or slower. So this is sort of, it's an assessment because it allows the students to use the rules that they use or that they've written out from the first activity and sort of test them out. So sort of self-assessing the rules that they wrote previously. And then they get to build the gear train in Gear Sketch and see whether their prediction was true or not. So I'll swap back to those gear trains in the assessment activity so we can take a look at those. Right here. So I think the most helpful way to look at the gear trains is to follow one gear at a time. And that would be the way that I would encourage students to do that as well. So if I have a clockwise gear, then I'll have counterclockwise, and then I will have clockwise, and then counter, and then clockwise, and then counterclockwise. So my prediction here is going to be that this last gear is going to be moving counterclockwise. And then the students are also asked to make a prediction whether it will be faster or slower. So again, they refer back to those gear rules that they wrote previously. And we said if a gear is bigger than the one next to it, that it's going to move more slowly. So we're going to predict that gear is going more slowly. And then again, we can put we can replicate this sort of gear train within Gear Sketch to test out those predictions. Now, the second gear train here. Now, again, we're asking the same thing. So what is this going clockwise, counterclockwise? And now we can also, we can use our prediction if we have an even number of gears, then the last one is going to be going opposite to the first. If we have an odd number of gears and it's going to be going the same direction as the first, we can use that rule. And we can also sort of test that by following each of the gears successively through the train. So if this one here is turning clockwise, then that means that that first one was actually turning counterclockwise. So I have counterclockwise, clockwise, counterclockwise, clockwise, counterclockwise. So we're going to predict that this last gear in the train is going counterclockwise. So if I want to double check that other gear rule about the odd and even, I can, do a quick count. 1, 2, 3, 4, 5, 6, 7. I've got 7 gears. So the first gear here, the second gear is going clockwise, but that means obviously that this one here was going counterclockwise. So if I have an odd number of gears, then the last gear in the train is going to be going in the same direction. So I can say that it should be going counterclockwise, and that's actually that same prediction. So that's good. So here we have sort of another gear train where again we're being asked to make the prediction here for the last one. And again, we're going to use that same sort of process of following. So here, this one is going to be going clockwise, and this one also clockwise. So this one here will also be going clockwise because it's sort of on top of it. And then we have counter, and then we have clockwise here. And we're going to, again, sort of make that comparison from the last one to the first one. And again, so the answers are all, we have provided them. So I won't go through this last one here, but a really nice extension to this activity would be to have students drawing their own gears. And obviously they can just use circles. So again, they don't have to draw the gear teeth. We don't really want to get into the number of gears or the number of teeth in that specific gear ratio, but look at sort of qualitative aspects of the way that the rules that gears follow. So they can create their own gear train and have someone else make a prediction based on that. So next day, we're going to go over the culminating math activity. So we're going to be using a free web-based program called Scratch. It uses a block-based coding language that we're going to be able to use to code gears. So we're going to take the rules that we have found in this sort of first inquiry-based activity, and then apply them into Scratch and make sure that our gears, the gear trains that we're going to program, are following the right rules. Because one of the things that you can do in Scratch is you can make rules or you can make gears that go against sort of the laws of physics, right? You can make a gear train where they all go in the same direction, and that's sort of not true to life. So we want to have, we want the gears to represent, like a real life scenario. So we're gonna look into Scratch. We're gonna take a little dive in there and see how we can use that program to code gears and continue with that prediction and pattern making. So I want to thank everyone for joining us today. All the resources are going to be online. We're going to also post the video. So the video right now is being recorded. It's going to be in the same location with the other bank of resources, as well as the presentation from today. Hopefully, we will see everyone tomorrow. If you have any questions, we would love to do our very best to answer them. We're, looking to help you integrate coding in your classroom. So if we need to, set up a video call or a phone call, or if there's something we can answer just via email, bring it on, bring it on. So I've got here a QR code for a survey if you have a few seconds. We're always looking for feedback about how we can improve these sessions, and so feedback is welcome. Feedback is a gift. So thank you very much again for tuning in, and hopefully we will see everyone virtually behind the scenes tomorrow. Send us questions. Take care.